All right. Can everybody see and hear me just fine? Assume so. Yep. Okay, cool, cool. All right, so yeah, we're starting chapter 5. Wow, we've come really far, really fast. So chapter 5, the title is Free Energy and Chemical Thermodynamics. So basically, we're going to develop some techniques that are going to be relevant to the types of stuff that you would want to talk about if you're going to do chemistry, if you're going to talk about like chemical reactions, specifically like on the surface of the Earth in some specific assumptions. So yeah, previously what we were talking about was we were talking about these idealized processes, right? Where if you've got like a PV diagram and you've got some engine that goes around in some loop and it comes back to the same point. So we talked about like cyclic processes. And in these processes, you start where you end, and so entropy overall is not changed for the system itself. But most processes are not actually like this, so not relevant for, we'll say, reactions. So for chemical reactions, obviously, like when two things combine or split apart or do some kind of reaction, they don't just start at one point, combine, and then break apart and come back to the same point. They break apart and then they just stay apart, or they come together and then they stay together. So we're going to stop talking about cyclic processes now. So the kinds of things that we want to look at that were relevant for chemical reactions are going to be the following situations. We're going to look at stuff where we're at constant temperature. So you can think of that as just being in like thermal contact with some bath. So if you've got like some solution in a beaker and you're looking at some kind of chemical reactions, you're at constant temperature because approximately the reaction isn't really changing the temperature of the water at all, because the water is so big compared to the molecules that are reacting. So we want to look at stuff that's at constant temperature. And we're also going to be on the surface of the Earth, and generally we're not applying any kind of extra pressure, so we're going to look at constant pressure situations at all. And so that is constrained via mechanical contact. So we want to develop framework for dealing with these types of things. Okay, so now we're going to come back to a notion that we kind of glossed over a little bit at the beginning, and that notion is enthalpy. So does anybody remember what enthalpy was? Anybody? Let's see, chat. U plus PV? Yes, that is right. Yeah. Yeah, so enthalpy, and do people remember why enthalpy was a useful definition for a state variable? So we know that it's defined as U plus PV, but do we remember why we wanted to do this? Yeah, let's see. Easier to work with in dust energy. Yeah, it's easier to work with, but in what types of situation? Yeah, I think we're getting closer. So it ignored a certain type of work. That's right. So specifically, enthalpy is useful when you have like a constant pressure situation. Yeah, Carter, you've got it. So yeah, this is the energy of the system, as always. And this you can think of as the energy to make room for it. So if you've gotten some environment and you want to make a particle, you need to put the energy in to actually make the particle itself. But if you're in some kind of environment and there's already stuff there, you need to move this stuff out of the way. So you can add this PV term to track that. And so what it turns out is that if you have like a constant pressure scenario, the P delta V terms will cancel. So you can just completely neglect that. It all gets taken into account in enthalpy. because like if you break down this U, right, by the first law of thermodynamics, if you look at delta H anyway, yeah, here I'll just write it out. So if we looked at like delta H, that would be equal to delta U plus P delta V. And if we're holding the pressure constant, right, so if this is a constant pressure scenario, then we only get this P delta V term. And so by the first law of thermo, we would just have that this delta U is the heat added plus the work done plus P delta V. And if the only kind of work done is like, well, we could break this down into like a adiabatic compression minus P delta V and some other type of work. So we showed this exact thing before, which is just that if you have constant pressure, these terms cancel out, and all you got to do now is just track these things. So it automatically takes into account the work that needs to be done to move the particle out of the way, and then you can just forget about it. So now we want to do the same kind of idea where we add in something that we get for free from the environment and apply it to a different type of scenario. And so specifically what we're going to talk about right now is going to be when we're in like a constant heat bath, basically. So let me make another page. So let's say we've got some kind of water solution, and we've got like molecules that are zipping around in here and whatnot, and they collide, make another one, whatever. There's some kind of chemical reactions going on in there, some kind of blocks. And these chemical reactions are really small compared to the water bath. So you can think of the water bath as just like a free heat source, because it can absorb heat into the reaction, and it can emit heat without changing the temperature of the bath. So effectively, in this type of situation, we're talking about constant temperature because we can get heat for free. And so we want to develop a new state variable that is relevant to these kind of constant temperature situations. And so what we're going to call this is going to be F, which is known as the Helmholtz free energy. And so what it's going to be is it's going to be the energy of the system just in and of itself. And then we'll subtract off the heat that we can get for free from the environment. So this is TS, where recall that Q is equal to T delta S. And in this case, we're just writing S right here because, well, here. So delta S is obviously equal to SF minus SI. But we just take this to be 0. And so we're only considering this right here. Yeah, I'm recording, Jacob. So this state variable right here, it takes into account the fact that we can get heat for free from the environment. Is everybody on board with that? Yeah, question. Mm-hmm. Yeah, so it takes into account the fact that you are in an environment where you can get this free energy from the environment itself. So this energy right here, this that comes in as heat from the bath or whatever it is, it's stuff that we can't actually extract or we can't put in. The environment is just going to put it in and take it out on its own. So in these types of situations, this is going to be like the relevant free energy. And that's why it's called the free energy, because it's the energy that you can get for free. Does that make sense? Okay, cool. All right, so now what we're going to do is we are going to, what I am going to call enthalpyize this right here. So take F and so what I mean here by enthalpyize is just we're going to now also take into account a situation where we could get like an enthalpy type version of this free energy. And so all we're going to have to do then to define this other state variable, we'll call it G, is take whatever this state variable is, and now we're going to take into account the possibility that we can add on this work term from the environment. So the environment either collapsing or expanding the space. And so what this guy is going to be called is the Gibbs free energy. So now overall, the Gibbs free energy, it takes into account the fact that we can, yeah, was somebody going to say something? No? Okay, that might have been an accident. So it takes into account F. So it takes into account the fact that we might be in some kind of heat bath where we're in a constant temperature environment. And now it's going to take into effect that maybe we're also in a constant pressure environment where we can also neglect this work that's going to be canceled out by the environment when we're either creating or destroying the system. So these are just two new variables which correspond to these two types of specific situations. And so if we were to write this out just a little bit more, we could write out F in terms of U minus TS. So U minus TS plus PV. So we could also rewrite this as H, the enthalpy, minus TS, which makes sense. And so altogether, we're going to refer to the set U, H, F, and G refer to as thermodynamic potentials. Yeah, Safe, what's your question? Mm-hmm. Yeah, exactly. So the whole idea is that, so if you're in a constant, so first of all, if you're in a constant temperature situation, the environment will either put in whatever this heat is for you, or it will take it out for you. And then the enthalpyized version is just if you're in a constant pressure environment as well, it can either provide that work to collapse the space, or it will provide the work to expand the space, right? So you get it, here you get heat for free, here you get heat and the compression work for free from the environment. So we're basically just neglecting whatever the environment is providing because that's the only thing that we can actually talk about and extract. Mm-hmm. I mean, it doesn't necessarily have to be this all or nothing thing, which we'll see in just a second. I mean, we can also talk about changes in these quantities itself. So, I mean, the particle can like still like change in size or something. And so there's still some kind of like expansion or compression, or reactions can happen where there's heat entering or leaving, right? So it doesn't have to be this like all or nothing, we're creating it or we're destroying it. These are still going to be relevant to whatever types of situations we think up. Does that make sense? And maybe it'll make more sense when we start working with it. Okay. So yeah, this set all together are thermodynamic potentials. And now at this point, you might be just like, your head is spinning because all of a sudden there are just so many different variables going on. We thought we just had the energy, which was the main state variable for the system, but now we've got all these different types of energy. But the point is that all these different types of energy just correspond to different scenarios. Like this is purely constant pressure, this is purely constant temperature, and then this is only relevant for constant temperature, constant pressure. So they apply to different things. So one nice way to remember these is via the mnemonic that's presented in Schroeder. So I also remember being taught this when I was taking thermo for the first time. So you've got this box, and if you can remember, this box is just U, F, H, G. Of course, the mnemonic is only as good as your ability to remember the mnemonic. But if you can remember this, then hopefully it'll make it a little bit easier. So think of it in this way. Minus TS to go that way. So basically the way to use this is if you want to recall how you go from the state variable, the energy of the system, and get to like the Gibbs free energy or the Helmholtz free energy or the enthalpy. If you want to go from here to here, you have to take U and then subtract TS. So if we go from there to there, then that would look like taking U minus TS, and that should be what F is. Okay, so that lines up with what we just said. And if you go from here to here, you should add PV, is what that's saying. So if we want to go down here, then we would take F plus PV, and that is G. And so like this, you can get from U to F to G, or you can get from U to H to G. And I suppose you could also go backwards as well if you wanted to. If you go backwards, you just subtract PV or add TS. So yeah, maybe this is kind of silly if you don't have any problem remembering it, but maybe for some people it'll help a little bit. Okay, so yeah, as Saif was alluding to, we won't want to just consider absolute destruction or creation. So we might want to look at just the change in all of these quantities. So for example, if we take F, which we have defined using this table right here, is what, U minus TS. And we just change everything that is allowed to change right here, which, keep in mind, this is defined for constant temperature, so the temperature cannot vary. So we would take delta of that, delta U minus, maybe if you're being naive, you might take delta of this whole thing, but then just using the distributive property, or the product rule, sorry. This would be delta T times S minus T delta S, since this is constant temperature. This term just goes away. And so using the first law of thermo, we can expand out this delta U, right? So we can write that as Q plus W minus T delta S. Okay, so now what we can say is that if there's no new entropy created in this process. Yeah, Jacob, what's your question? You're good. What was that? You cut out. Hello? Did I just cut off from everybody? Oh. So I didn't hear like half of that, Jacob. I don't know why you cut out. Yeah, I can. I heard you start stating your question and then you came back in as soon as you finished. Oh yeah. So well, it's actually P delta V, right? So let's say here we are. We've got our environment, it's filled with air, and we want to take this and we want to create a system that has volume V. Yeah. Yes. No, it's okay. So yeah, I mean, it's just because like you need to move this stuff out of the way, and the volume that you need to move is like this volume V. So like delta V here is VF minus VI, but VI is just 0, so it's just V. Yeah. And same thing for like TS here. Like that's actually a T delta S, but we're just taking it to have 0 entropy initially, right? Because it's just non-existent initially. So no, that's actually a good question. It might clarify some things for some people. Okay, what was I saying? So yeah, so I was saying that if there's no new entropy created, then the second law tells us that we have the perfect equality, not the inequality, that Q is equal to T delta S. That's the best we could possibly do. And if that's the case, then obviously this term and this term cancel. And so we have that delta F is equal to the work done. So this is specifically no new entropy. Well, we know that in general, entropy can get created. So if there is entropy created, we want some kind of inequality here. And so, again, by the first law, we should just have that T delta S is greater than or equal to Q. We just looked at the equal then case right there. So now we can write the inequality as just that change in F is going to have to be less than or equal to W, right? Just by the first law. So this is for constant temperature, remember. And this is a result to remember. Okay. Oh, whoa. Okay. So now if we don't want to track the expansion and compression, we can consider the Gibbs free energy. Okay, so let's take P, and can we take a quick peek at the previous slide? Yeah, absolutely. If I'm ever moving too fast, just holler. Let me know when you're done peeking at the slide. Yeah, absolutely. Oh, that's a good question. So this work at this point in time, it can be anything. But you could just break it down into like what you call like other work and compression work, like quasi-static compression work. So you could break this down into like W other plus, or I guess minus, P delta V, right? And so what we're actually about to see is that you're going to want to do this kind of breaking up if you're going to talk about like the enthalpy version of F, or the Gibbs free energy, because then this will cancel out, and all you have is that the change in the Gibbs free energy is just tracking the work that's done other than the compression work. Oh, it could be anything. I mean, like electrical work is like a common one. Stuff that is going in some other way that isn't compression and expansion. It could be literally anything. Okay. All right, so yeah, now we are going to not want to care about the expression compression, so we're going to talk about the constant pressure, constant temperature environment. So these are now constants. So if they are constants, well, then I should restate the definition. So G is what? Let's remember using our formula right here. So if we want to get to G from U, we could go either way. So we could take U plus V minus TS, right? Or G is F plus PV. So if we use that and we take delta on G, we would have delta U minus T delta S plus P delta V. And we don't have deltas of T's or deltas of P's, right? Because P and T are held constant at this point. So now again, if we use the first law, we can break up this delta U into the heat added to the system plus the work done, includes every type of work done, minus T delta S plus P delta V. But now we can just, oh, well, one more step. So again, we can use the second law, and we can state the fact that when you add these two pieces together, they have to be less than or equal to 0. What did I want to say here? Oh, yeah. So we'll just group those together. So this piece is less than or equal to 0. And we can also break up this work right here into what I was just saying before. So work other, whatever other type of work exists other than compression work, and whatever our quasi-static compression work is, so minus P delta V. And then we're going to add P delta V. And so again, we see that if we take the enthalpy version of F, which is G, the Gibbs free energy, then this part just cancels out. And all we're left with at the end of the day is Q minus T delta S plus the other work. And we know that, yeah, this is less than or equal to 0, which I've written 1,000 times now. And so we can say the inequality is going to be true, which is that delta G, the change in G, is going to be less than or equal to other work done on the system. So this is for T and P constant. Okay, so this displays to us why this definition of the Gibbs free energy is useful, because now when we talk about the change in Gibbs free energy for chemical reactions and whatnot, the only thing we need to worry about is the actual work that we are putting in, the work that's being done other than all of the work that the environment is providing or the heat that's providing. Okay, so that's why this is so useful for chemical reactions. Because these types of things are generally going to be situations where you are going to be holding the temperature and the pressure constant. Okay, so those are things that you can't actually provide yourself. They're just being provided by the environment or taken away by the environment. So you might now ask, how would you measure G? Okay, well, what you could do first is we could measure delta H, the change in the enthalpy. So that is just going to be delta U plus P delta V. And if we expand that out, again, we're just going to cancel out the minus P delta V there with P delta V there. So this will just become the heat added plus other work done. So what you could do is you could allow some kind of process to happen, don't do any other work on the system, so that's 0. And then you can find what delta H is by just tracking how much heat you have to add. Okay, so that could get you delta H. Then you could, for example, calculate the initial and final entropy from the initial and final state. So you could calculate delta S by just doing this integral if you happen to know what the specific heat at constant volume is. And so you could get that if you know this. And then the third step is you could just take these quantities, use the fact that you know that delta G is equal to delta H minus T delta S, which we could show right here, right? Like this plus that is delta H, and then this is just the minus T delta S right there. And so if you can calculate these two quantities, then, well, you've got delta G. So that's how you would do that. I think I've got an example coming up soon. Oh yeah, so little comment here. So you might ask, like, what is the absolute value of F or G, right? Like here we're talking about changes and whatnot, but how do you actually calculate what it is at a certain point? In practice, this is going to be impossible to do. Because you need to calculate like the rest energies plus the interaction energies plus whatever type of other energies there are in the system. So you would have to do like mc squared for all the particles plus like all the interactions plus whatever else there is. And God, we don't want to do that. So in general, what we're going to do is we're just going to specify F and G like some reference value at some specific point. And then in general, all we're going to care about is the change in these two. So actually the reference point is going to be completely irrelevant when we compare reactions to each other. So that's just that. So here we're going to see exactly how this plays out with an example. So let's do the example that's listed in the book, which is just taking nitrogen plus hydrogen and getting ammonia. And if you have your book out right now, it might be a useful exercise to look in the back at the table. Where is the table? I think it's like page... It is page 404. So if you wanted to follow along right now, you could. So the exact chemical reaction that's happening here is that you've got N2 plus 3H2 goes to 2NH3. And so we're going to consider this at room temperature, so 298 Kelvin, and a pressure of 1 bar, which is just basically, is exactly actually, well, no, it's approximately what atmosphere is, 1 times 10 to the 5 pascals. So what we're going to do is we're going to use the table in the back to compute what delta G is for this reaction. So we're going to compute the change in the Gibbs free energy for going from this state to this state. So if we look at the table on page 404 and 405, you can find all of these values specified. And one thing that you might see that you might be curious about is the fact that you always see this delta. So if you see like delta H, it's not just straight up delta H, there's an F right here. So that F, from what I had read, looks like it is assuming that you have, that you're starting with that, like this delta is going from starting with like the elemental form of whatever this is. So it's talking about like going from N2 to like whatever the stable form of it is. So for example, if we pull out what H2 is from the table, it gives us that delta F. H is 0 because it just automatically, it's already existing in its elemental form. So if you sit H2 into the environment, it doesn't change at all. It's just already there. So this is just 0. One can calculate the entropy, and here it's just given in a table. So it's 130.68 joules per Kelvin. And again, it's already in its elemental form. So delta Fg is again just 0. Nothing changes. Again, for nitrogen now, you could probably guess this. So this is also 0. In this case, S is 191.61 joules per Kelvin. And again, this is just going to be 0. Now, the only one that's not going to be 0 is obviously going to be the thing that is made, the ammonia, on the right-hand side. So if you start with elemental form of this, it has to change in order to turn into ammonia. So now this delta F is given in the table as minus 46.11 kilojoules. And can anybody tell me the significance of this negative sign right here? What should we infer if we see a negative sign assigned to something in this particle or in this table right here? Yeah, so it'll need energy to be broken down. Another way of saying that is just that if you put these two things in a solution, that they will just automatically, they will tend toward reacting into ammonia, right? Because they're going to try to, well, we haven't talked about this exactly yet, but they're going to try to reduce this this enthalpy right here. But yeah, that's right. So you'll have to put energy in order to break this apart into its constituents. So the entropy is also calculated to be 192.45 joules per Kelvin. And the Gibbs free energy change is minus 16.45 kilojoules. And again, this is negative for the same reasons that I just mentioned. So now what we're going to do is we're going to calculate delta G from this table right here. I'll try to do it over here without running out of space. Okay, so we've got that delta G is delta H minus T delta S, right? So if we take all of our delta H's, what does a positive del H mean? Yeah, so a positive del H means that you would have to put energy in order to make that thing, which just means the opposite. So here it means that it's just going to, you're going to need to put energy in to break it apart. If it's a positive delta H, you need to put energy in to make it, and vice versa for breaking it apart. Does that help, Jacob? I'll assume so. Okay, so here we're going to take this chemical reaction and we've looked up what delta G should be. Now we're going to show that we can actually calculate it to be that given these delta H's and the delta S's right here. So we know our answer. We just want to make sure that we're doing this all correctly and we can use the tables at our disposal. So we have 2 times minus 46.11 kilojoules minus 0. So this is delta H. And then we've got minus 298 Kelvin. So that's our temperature that we're working at. And note that this is 0 right here just because all of this is 0. So we're just taking the 2 ammonia right here. This is our final state. This is our initial state. So delta H was 0 there. Now we're taking T delta S. So here we're going to take, there are 2 ammonia. So we need 2 times whatever that change in entropy is. So it'd be 2 times 192.45 joules per Kelvin minus 3 times the hydrogen's value, 130.68 joules per Kelvin, and then minus 1 times the nitrogen's value, joules per Kelvin. Okay, so if you plug that all in your calculator, what do you find? You find minus 32.99 kilojoules. You're like, wait a second, that's not this. Well, we have 2 ammonia being created here. So you divide that by 2, and you get exactly this result right here. So it seems like our method for calculating delta G is working, given all of the values in this table are actually correct. So does that make sense to everybody? Does that seem fairly straightforward? Yeah. Yeah. Yes. Yeah, absolutely. Yeah, so if it's negative, well, we're going to discuss that a little bit later on. When what we're going to do is we're going to translate the second law of thermodynamics into like how H and G and F change. And basically what we'll find is that the second law of thermodynamics translates into minimizing G, so making it more negative. So hopefully, I think that should answer your question. But we haven't quite gotten to that yet, but you're seeing the right things here. Okie dokie. So now we've got something we can actually calculate that we talked about before. So we're going to talk about the section electrolysis, fuel cells, and batteries. So let's break down electrolysis. We'll break down delta G for the reaction. It's just water being split up into hydrogen and oxygen. This process is just known as electrolysis. And it is how you would make hydrogen in order to put it into a hydrogen fuel cell. And then the opposite thing happens when you burn hydrogen, right? So you take hydrogen, combine it with oxygen, it burns, produces a bunch of energy, turns into water. Okay, so if we again, oh yeah, okay, yeah, that was a private message, yeah, go ahead. Okay, so if we look at the table again, table on page 404 and 405, we would see that for formation of water, we should have that delta FH is equal to minus 285.83 kilojoules. So that would be for having hydrogen and oxygen and going the other way, right? And that makes sense because these things we typically think of as wanting to come together to make water. So if we go opposite direction, we can say that heat out via burning will yield us plus 285.8 kilojoules. So yeah, this would be the energy you could get out by burning hydrogen with oxygen. Okay, so therefore to form H2 and 1/2 O2 out of H2O, we are going to need to put in 285.8 kilojoules of energy. Okay, so some of this must be delegated to making room for the gases. And so if we look up in the back, we can find out what delta V is for this. We find that would be P delta V is equal to 4 kilojoules of energy or work. And then the rest, which should be approximately 282 joules, kilojoules, it will need to go into the system. So the question is, in what form is it going to go into the system? So let's look at the exchange in entropy, since this is going to relate to the heat that has to go in the system. So look at delta S. So let's look in our table. We can find the entropy of water, or H2O in its liquid state. It is 70 joules per Kelvin. We look at the entropy for hydrogen as a gas. It is 131 joules per Kelvin. And do note that when you're looking in these tables, you need to be careful because they do list like several different forms for like H2O. So if you just accidentally glance at it and you're like, oh, 2 H2Os, I'll just use the first one. One of them has a parentheses and an L, one of them has a parentheses and a G, so that corresponds to the liquid and the gaseous phase of the whatever that molecule is. So that's hydrogen, and this would be oxygen. 205 we'll just leave that off. Joules per Kelvin. So our initial entropy would be what? It'll be this guy right here, right? It's the hydrogen. We're starting off with hydrogen, turning it into these two. So this would be 70 joules per Kelvin. Das final would be the sum of these two. That would be 131 plus 2 1/2 205. It's a half of what O2 is listed as. It's just a single oxygen. And that is also joules per Kelvin. And so we can find that delta S is plus 163 joules per Kelvin. So we gain entropy by breaking up water into its constituents. Would like to have that all on one page, but oh well. Okay, so therefore we're going to have that the maximum energy that enters is heat. Is going to be T delta S, right? Because that's our thermodynamic, our second law of thermodynamics, which is that this, when no new entropy is created, these two things are equal. So we just calculate what delta S is. We know what the temperature is. So the most we can get from the system for free, if we were in a constant temperature bath, is going to be this 49 kilojoules of energy. So leftover energy, which enters as work, must be what we had previously, which was 286. Let's go back. Oh God. Flipped ahead to like the first slide accidentally. Yeah, so the 286 is coming from this guy right here, which we were just rounding up. So that's what we started with. We just showed that we can get this much heat for free, so we subtract off that 49 kilojoules, and that gives us 237 kilojoules. So this was the free heat that we get. And this ends up being precisely what delta G is. Okay, so delta G is equal to delta H minus T delta S, which is exactly what we just calculated. So again, we're seeing that delta G is the energy that we can get out of a system. So in this case, the best that we can possibly get out of splitting apart the system right here is this 237 joules. And so if you want to talk about like how efficient a hydrogen fuel cell is, you could write this down in the form that we were talking about previously. So you could write the efficiency as the benefit over the cost. So in this case, our benefit would be the most that we could possibly get out, the 237 joules, over the initial starting point, the 286. And this should be approximately 83% efficiency. So the best you can possibly do with a hydrogen fuel cell is roughly 83% efficiency, which is really, really good compared to internal combustion, as we were talking about previously, where like internal combustion is like 30% at best. Okay, so now let's go in the other direction. Burning hydrogen. And so burning is just this chemical reaction right here, where you take H2, put it together with O2, gives you water. So like we just said, if you want to burn it, you can get 237 kilojoules of work. And all these calculations were done for a single mole, so this is per mole. Just elaborating on what I said previously. And if we were all in person right now, it would have been fun to get like a hydrogen balloon and blow it up in class. I remember having a demonstration like that done for me when I was taking like an intro astronomy course, just to feel the sheer heat that comes off of that thing. But obviously we can't do that right now, but just know that I would have liked to. Okay, yeah, there's another little section talking about the same kind of idea, the same process for calculating the change in the Gibbs free energy for the lead-acid battery. That's on page 154 and 155, so if you want extra practice on calculating this, it's basically the same thing. So I'm not going to go through it again just because you're basically just pulling calculations from the table and throwing them in. Okay, so we've got a little bit of time left, so I'm going to try to just introduce this last section, which is now we're going to form new thermodynamic identities from these new potentials that we have. So previously, you might remember that we had derived that du could be related to the change in entropy times T minus the change in volume times P plus the change in number of particles times mu. So we're now going to write something similar. For H, F, and G. Okay, so first we're going to work with H. Okay, so for H, let's consider that we take the expression for H. Remember that H didn't necessarily have to assume that the pressure was constant. It was just useful when the pressure was constant. So we can consider all of the things in it changing. So we're going to consider the energy can change, pressure can change, and the volume can change by some amount. So if we do this, we can calculate dH. So dH would be du plus pdv. Here, I'll write this out explicitly. d on pv plus v dp plus p dv. Yeah. Okay, now if we expand out this du using the first law of thermodynamics as we always do, we can rewrite that. Or sorry, not using the first law of thermodynamics, using the thermodynamic identity that we have right here relating it to ds, dv, and dn. So we can rewrite this du as t ds minus p dv plus mu dn plus p dv plus v dp. Okay, so now we see that if we expand that out, we can cancel out this p dv with that p dv. And we just have that TDS plus mu dn plus v dp is equal to dH. So this is the first new thermodynamic identity that we're going to describe. And all we're doing is just taking the definition for the enthalpy, varying it with respect to its variables, and then using the previous thermodynamic identity to get it into a form that looks something like what we had before in terms of the previous thermodynamic identity. So now you can use this identity to derive relationships for like t, mu, and v in terms of partial derivatives on h, for example. So from here, you could get, that what t, if we hold n and p constant, would be del h over del s. So that would be with n and p held constant. We could get mu by holding s and p constant. It's equal to, would be del h over del n with s and p constant. And we could also get a relation for the volume with s and n held constant. And how this is going to be useful is like generally, so the examples that we had just worked through gave us in a table the value for like h at a particular value for a specific kind of environment, like, right? So it gave you like h at room temperature and atmospheric pressure. But if you want to calculate something at a different like non-standard temperature, you're going to need to use these relationships right here, because like if you know, for example, I don't know, if you want to find like the slope of h with respect to the pressure, if you want to find it at a non-standard pressure, you could integrate this relationship. You can get it at a different pressure if you know it at a certain one. Okay, so you can use these relationships right here to get the stuff that you find in a table and put it into a different environment, basically. Okay, so there are two more thermodynamic entities that we need to derive for F and G. We got H done. So we are 2 minutes over. I might just finish that up quick if nobody minds. Does anybody mind if we just finish up these thermodynamic entities? Okay, cool. It's really just algebra at this point, so I don't think people are really going to struggle with this. So the second is that we're going to work with F. Okay, so as we always do, take the differential on F, Helmholtz free energy. That will be du minus t ds minus s dt. Again, just using our original thermodynamic identity for du, we can write this as t ds minus p dv plus mu dn minus t ds minus s dt. And this time, what we have cancel out is this term. And so our identity just looks like this. So it'll be minus s dt minus p dv plus mu dn. So there's another. And then from this, we can derive its three relationships. So we could get minus s is equal to del f, del t. That doesn't look like an f. With v and n held constant, we could get this one, which relates minus p to the derivative of f with respect to v with t and n held constant. And we could also get this one for the chemical potential. Okay, so that's that. Now we just got one more left. So let's work with G. Again, take the differential on G. Get du minus t ds minus s dt plus p dv plus v dp. Gets pretty long. Now we want to expand out the du, so okay, let's just do this all over again, just for the sake of everybody seeing it. Minus t ds minus s dt plus p dv, plus v dp. All right, so now for the enthalpized version of the Helmholtz free energy or the Gibbs free energy, we have this term cancels, so the TDS cancels, and the PdV cancels, which is basically what we'd expect. So the relationship that we get for dg is that it is related to minus s dt plus v dp plus mu dn. That is dg. And you can use this to get non-standard forms for G in different environments. So get minus S del G over del T. So if you knew the entropy, you could find this at some other temperature. If you knew the volume, you could find G at some other pressure. And if you knew the chemical potential somewhere, you could find G at some other number density other than 1 mole, which is just given in the back. All right, so that was long, a little bit tedious, maybe a little boring, and now you've just got like a bunch of new state variables, a bunch of new thermodynamic identities, but just realize that they're not that complicated. They only exist because we live on the planet Earth and we do chemical reactions in a certain way in certain types of environments, so that's why we thought of these things. I do have a bit of an aside that I'd like to go through to kind of detail. I know people are probably getting sick of this by this point. Okay, so I wanted to detail an analogy between classical mechanics and thermodynamics, because the reason for doing these kinds of transformations relates to something called a Legendre transformation. I don't know if people are very familiar with that or not. Maybe from classical mechanics, where you transfer from the Lagrangian formalism to the Hamiltonian formalism. Is anybody familiar with that? Where you start off with a Lagrangian that's defined in terms of so you've got like L as a function of Q and Q dots and positions and velocities, right? Yeah, okay, I see some yees, some yas. So what you do in classical mechanics is you have some Lagrangian and you perform this thing called a Legendre transform, which is where you take the velocity, you multiply it by this thing that you call the conjugate momentum, which is defined as this right here, and then you subtract off the Lagrangian again, and this defines something that you call the Hamiltonian, right? And so the whole point of doing this is you're changing variables from something as a function of Q and Q dot to something that is only a function of Q and this new thing that you've defined, P, the momentum. So effectively what this is doing is it's taking this Q dot and it's turning it into a new state variable, P. Okay, so this is the idea of a Legendre transform. So now, basically what we're doing now is we're taking U, which is originally a function of S, P, and N. So the energy of a system was a function of the entropy, the volume, and the number of particles. And for example, for like enthalpy, we're taking it and we're redefining this other thing that we call the enthalpy, which ends up just being now a function of S, P, and N. So what enthalpy does is it takes one of our state variables, the volume, and it turns it into a different one, which we now call the pressure. So this is just another way of implementing this kind of thing called a Legendre transform. So I just want you to put what we're doing right now into the context of what you've possibly seen before in classical mechanics. Yeah, you can do similarly for F and G. Okie doke. That is all I want to talk about right now. I'm sure it's all you want to talk about at this point too. So are there any questions about anything, or should we call it? Looks like everybody's sufficiently bored or confused or annoyed. I don't know. How's everybody doing? Thumbs up. Okay, cool. All right. Well, yeah, if there are no questions, we can talk more next time. I'll have office hours right now until 3, so join if you want to chat. Okay. Yeah, we'll see you on Tuesday or Wednesday. Thanks.